Okay. All right. So we now go into ANOVA. So ANOVA is a way of comparing the means of, is a test that's used in comparing the means of continuous, a continuous variable across more than two groups. So when you have more than two groups, or and you are comparing continuous data, you use ANOVA. For ANOVA also, you have a number of assumptions that need to be satisfied. The data needs to be, the continuous variable you are testing needs to be normally distributed. Obviously, it has to be continuous variables, and then the variances need to be equal as well across the three groups. I'm sure they mentioned a word like homoscedasticity in class. So that's basically some of the assumptions that need to be satisfied. So for this, we're going to use the dataset bptrial.csv. So I'm going to go into SPSS now and import that data. Let's see. Okay. So I'm going to go to so ion trial, yeah. Okay. Yeah, whatever. Finish. Okay. So this is the ion trial data set. We have the hemoglobin value. We have treatment groups. So here we have group 1, group 0. Sorry, I think I'm looking at the wrong data set. I'll just go off camera for a second. Sorry again, need to proceed.
I think you're meant to import BP trial.
Not import BP trial. BP trial, not ion trial.
Hello. Sorry. So I think imported the wrong data set. So coming here, BP trial, open. Okay. So can we see the BP trial data set?
Yeah.
All right. So you can see that some of them have received a placebo, some of them have received old drug Y, and some of them have received the new drug X. So we're going to be comparing these three groups of participants, those that received the placebo, those that received the old drug, and those that received the new drug. So ANOVA is kind of similar to the independent test. It's just that it's done across more than two groups. We'll see why in a minute. So we go to analyze, compare means, and we come to one-way ANOVA. And our dependent variable is the systolic BP, and the factor that we're using, that's the categorizing variable, is treatment. So this has already been categorized, it has already been coded as a categorical variable. So we don't really need to do anything anything more. But then when you come to post hoc, are you all seeing this, or am I going too fast?
We can see.
You can see.
You can see,
All
but
right.
you're going too fast, sir.
Okay, so I'll start again.
Yes, sir. Thank you, sir.
So we have three different categories: placebo, old drug, new drug. And then we come to analyze, come to compare means, and then we come to one-way ANOVA. So our variable of interest, the variable that we are comparing across the three groups, is systolic BP. And the variable that we are using to categorize them, what we are using to categorize them is this variable called treatment. So this treatment variable is the one that is categorized into placebo, old drug, new drug. And we are using as the factor for the categorizing variable. In ANOVA, so let's just do that and look at outputs. We click on OK, and then it shows us this output. Let me just enlarge the screen. Take this out of the way. So the Anova test here is just showing us some. If you just go ahead and do the Anova test, it will show you whether there is a difference between the groups and also within the groups, but it doesn't really tell you where the difference lies. So we have three groups. Group one is no placebo, group two is old drug, and then we have new drug. So if you look at this first row, it shows you this is the F statistic. So this is the statistic that is calculated by ANOVA, and this is the significance. So looking at this, there is a statistically significant difference between those that received placebo, those that received what's it called now, old drug, and those that received new drug. But then we are not sure where exactly the difference lies. Is the difference between those that received the old drug and new drug? Is it between placebo and new drug, or is it between placebo and old drug? So in order to know, to find out this difference, there are these things called post hoc tests that we do on ANOVA. One such test that was discussed with you in class was the Bonferroni test. And in order to do that, we go back to the data set and analyze. So we come here, analyze, compare means, come to one-way ANOVA. Everything else is as it was, but then we come to post hoc and we click on Bonferroni. Okay. and then we go ahead and click on continue. So a lot of these other tests are also used used for similar purposes, but then we're interested in Bonferroni at this time. Options. So if you come to the options, you can click on homogeneity of variance test, and this will show us an output of the Levin's test, just like we saw in the T-test. This is giving us the confidence level. And then we click on OK. We enlarge that. So this time around, we have some additional data, including the test of homogeneity of variance. Based on the mean is what we're interested in. And the Levin's statistic is 1.1, not very important. What's important is the significance. So this significance is not statistically significant, which means that the variances are essentially the same because the difference between them is not statistically significant. So it means Anova test is valid. This ANOVA effect sizes is what this post hoc test rather is the output that came from our modifications there. This is the result of the Bonferroni. You can see it here that the Bonferroni test has applied. So I'm just going to go back into the data set to see what these different codes mean. So 0 is, I believe 0 is placebo. 0 is placebo. 1 is the old drug. 2 is the new drug. So let's go back to the output. So now when you compare the way you can interpret this is by looking at 0. Here is the variable that the group you are comparing against the other two groups. So we are comparing placebo against old drug and new drug. So comparing placebo to old drug, we can see that there is a statistically significant difference between the placebo and old drug. When we come here, we're also looking at placebo versus new drug. And when you come here, come down to the significance column, you can see that the difference is statistically significant. And then when you come here also, well, we have already, some of them are duplicate results because we have already compared 0 versus 1. So looking at 0 versus 2, we're also seeing that it's statistically significant. And then coming to this row also, 2 versus 0 is statistically significant, 2 versus 1 is statistically significant. So basically, all the different mean blood pressures are different. All the mean blood pressures are different across the 3 different groups. But then that's alone is not enough. We need to know which one is greater than which. So we come here and we look at the comparison between the placebo and the old drug. So the old drug brings about a decrease in blood pressure of around 37.9 millimeters of mercury, and this is the confidence interval for that. Then the new drug compared to placebo brings about a mean blood pressure drop of 47.5 millimeters of mercury. So going by this data, the new drug is more effective than the old drug in reducing blood pressure. But then we can go ahead also and compare the new drug and old drug. So what's the difference between two? This is one is the old drug, two is the new drug. So if you are subtracting the new drug from the old drug, you have an average of 9.6 millimeters of mercury, which means that on average, the new drug will give you more a larger drop in BP by this magnitude, and that's the confidence interval. And if you look at the old drug versus placebo, if you subtract placebo from old drug, you can see that the BP, you are subtracting something that is larger from something that is smaller. And that's why you have a negative sign. So it just means that the BP in people who receive the placebo is greater than those who receive the old drug. So it's just a reverse of this. You can see that it's 1 and 0 and 0 and 1 are the same. It's just the sign that is different. So I'm hoping that my explanation was clear enough, but if you have any questions, please ask.
Sorry, I missed the interpretation of the ANOVA effect sizes.
Okay. Is that Victor?
Yes, that's it.
Oh, okay. So,
No,
were
sorry,
you, yes?
I say it's not Victor. I just raised my hand. It's another person for now.
Okay, Victor, what's your question?
The interpretation you gave on the mean difference between the placebo and the old drug, which gave us a mean difference of -3 at 7.89. So I'm looking at that column, the entire column on top of it. The title I'm seeing there is 1 minus J, and I'm seeing that the 1 here they means treatment, and I'm seeing that J here means, 1 means treatment, and then J also means treatment. So I wasn't quite sure why we had to subtract placebo here from old treatment.
So this this treatment, this TRT, right, is a variable. I think you will understand it better when I go back to the data set. So in the data set, if you look at the variable view, you have a variable called treatment, okay?
Yes, sir.
And this treatment variable is a categorical variable, nominal. If you look at the values, okay, what's happening here? Okay, it seems the value labels were not defined. But if you come in here on the data view, where is this now? If you come in here on the data view, you will see the definition of the values for this variable. Okay, so the a value of 0 means that placebo was given.
Yes, sir.
For this variable treatment, this variable treatment can take either a value of 0, a value of 1, or a value of 2. So if you come to the outputs and you are seeing treatment, where is it? And you are seeing treatment here on top, it doesn't mean that all of them were just subtracting the same group from the same group. We're not subtracting treatment group from treatment group. Okay. So for the treatment variable, we're subtracting group 1 from group 0, which means we are subtracting treatment 1, which is old treatment, from placebo. Does it make sense now?
Yes, it does.
And then on this row, we are subtracting new treatment from placebo.
Yes, sir.
Yeah. Then when you come here, when you come to the second row, you are now flipping it. You are subtracting. This is new treatment.
Okay.
This is old treatment. If you subtract old treatment and placebo from old treatment, you are going to get the same numerical value, but the sign will change because the BP for placebo people who are not taking any medicine is higher than the BP for the treatment group one, old treatment and new treatment. Does it make sense?
Yes, it does.
All right. So that's the reason why the sign is negative here.
Thank you. Thank you, sir.
What someone else asked the question before you. I can't remember what the question was. Okay, you said the interpretation of the, you wanted me to go up over the interpretation of these differences between the effect sizes again.
You should explain
my question was the interpretation of the ANOVA effect sizes.
Yes.
The network went off, not the post hoc test. I got the interpretation of the post hoc test.
Okay. Okay, this effect sizes. Well, let me see. Point estimate, blah blah blah. It's been a while since I used this, so I can't really give you a ready-made answer right now. But I can look it up and send it on the email thread if that's okay.
Okay, thank
you. Okay.
So the most important interpretation here is that of the post hoc test in this output.
Yes. So this post hoc test and the this ANOVA. So the ANOVA, like I said, tells you whether there is a difference between these groups, and you can see the significance here. So if there is a difference, you can go ahead and do the post hoc test.
All right.
To check where the difference lies. So there are times when you do a post hoc test in ANOVA, and some of these combinations, some of these permutations will give you non-significance. So you can then zero in on the groups where there is a significant, statistically significant difference in reporting the results. But then even, I would just like to remind us that even as we are looking at all these things where we say it is statistically significant, it's not statistically significant, there is a difference between statistical significance and clinical significance. So sometimes you might find a result that is not statistically significant. For example, if you say hand washing can prevent if you improve hand washing techniques, it can prevent 5 deaths per month, maybe, from surgical infections. And then you do the statistical test, but it's not statistically significant. So yes, on paper, it's not statistically significant, but then preventing 5 deaths per month is clinically significant. So I'm just throwing that out there as a reminder.
Sorry, sir, I didn't get that. I'm sorry.
So I'm saying that this result for any test you are doing, whether T-test, whether it's one sample T-test, paired sample T-test, 2 independent sample T-test, ANOVA or chi-square or any other test that we're going to be doing in the future, you should, as you are looking at the statistical significance, you should also be thinking about the clinical significance. So the difference you are finding might not be statistically significant, but then clinically for you in practice, that difference is good enough for you to switch practices or for you to switch to the new intervention.
Okay, sir.
Is that clear now? Abdullah Ocean, what's your question?
Hello, thank you, sir. My question is that, does it now mean that for us to determine if our result is clinically significant, it has to be on our own reasoning, and there's no other way to prove it? Okay, all right.
It's based on a whole lot of other things, like obviously most people doing this kind of research are experts in their field. So based on what you have been seeing, based on other data available from other research and other evidence available to you, if that difference is clinically significant, you'll be able to make your own judgment on that.
Thank you, sir.
Yeah, you're welcome. So let me just go there. Yes, so these are the outputs that we just received from the ANOVA. So this brings us to the end of today's practical session. If there are no further questions, then I believe it's a good place to stop. We have gone a few minutes over the scheduled end time, but then okay, so 2 people have raised their hands, so I'll take these 2 questions, and I'm going to have to wrap up after that. As you can see, I've been receiving some calls, and right now I'm actually needed at the clinic. So for some reason, okay, Abdullah, you have not put down your hand before. Okay. Molly, what's your question?
Okay, my question is just basically when we started off with the T-test, and while we're trying to run our analysis, we set our test value for 30. So I wanted to know the rationale behind the 30 mark we used.
Oh, that is arbitrary. So it's the hypothesis of the people that did that research. Their hypothesis was that the what do you call it? The average age of the resident doctors is 30 years old. So they tested that hypothesis using the one sample T-test.
Okay, so it's not a fixed mark.
No, it's not a fixed value.
Okay, thank you.
You're welcome. Did I see another hand raised? Victor, are you raising your hand?
Yes, sir, but not for questions, sir.
Okay.
Yes, sir, I just want to say thank you, and also plead that we get the recordings of the class in our email, sir.
Okay, the class is being recorded, and I believe that it will be shared with everyone.
All right, thank you very much.
And you'll be able to have recordings of the previous class as well.
Yes, sir. Thank you, sir.
You're welcome. All right. Thank you very much for coming. Thank you, Stats Clinic, for organizing the class. I've learned as much from you as you have learned from me, and see you again in the next session.